Let's build a program to search images in your computer by text or even other images in less than 25 minutes. In order to build an image searching program, we have to implement these two steps. The first one is to build a nearest neighbors index, also commonly called vector DB these days. We'll use a multimodal neural network such as CLIP, which can take both text and image as its input, and then it can generate the embeddings. So these embeddings will be used to create the nearest neighbors index. Secondly, we will use the index to perform real-time search. So let's now look at the index building step. This implementation will look at the folder where you have images, and then it will take the images and pass it through this CLIP model, this neural network model, to generate the embeddings. And once we have the embeddings, we will use the embeddings, and along with the embeddings and the metadata, we will create this nearest neighbors index. So image metadata here will just contain the path of the image. So basically you can imagine every entry in this index to be a path of the image and the corresponding embeddings of that image. And we will save those both of these together into the disk, which we will later on use during the inference. So for uses during the inference, of course, we have to load the model and the index in memory. And once we have that, when a user query comes in, whether it's text or image, we will pre-process and then pass it through the model. The model will give us the query vector or embeddings. And using these embeddings, we will search in our nearest neighbors index. So this index will give us similar items in its database, right? So once we have retrieved the similar images, then we will display that in the UI. So this is the high-level overview of the implementation that we are going to do today. So let's dive in. To get started, first you'll need a few libraries that you have to install. We'll be using easyknn as a sort of a vector database to do this nearest neighbors searching. Then we need sentence transformers, datasets, and torch. I've already installed, but if you haven't, then you have to run this command. So as I mentioned, our implementation shall look at the folder with images, right? And then it should generate the embeddings and also create the nearest neighbors index. So for that purpose, I already have a folder with images. So here I have about 1,033 images. So these JPEGs are my own images, and these PNGs are from a dataset that I downloaded. If you have the images in a folder that you want to use, then it's you can go ahead with that. Or if you want to download some images off the internet, then this is the code that I use to generate these PNG images. So I'm using this diffusion DB dataset from Hugging Face Hub, and the split that I used was or the subset that I used was this last random 1K. So I have about 1,000 images from this dataset, and just to throw in some variety, I also added some of my own images here. So most of these are flowers, and these are some images from the Hugging Face dataset. So now that we have looked at the images, let's get started with the implementation. First, I will show you a few things about the model itself. The model that we're going to use today is called CLIP, and it's pretty easy to use using the sentence transformers library. So here's how we load the model. So the model I've already downloaded, so it didn't print anything here, but otherwise if you're downloading this model for the first time, you will see some progress bar here as well. And since I have a GPU, this model was loaded into the GPU automatically by this library as well. But it doesn't matter if it's in GPU or CPU, the approach we're going to use will work just fine. As I mentioned before, this model is a multimodal model. So this has multiple modalities, as in it can accept both text and image as input and generate the embeddings, right? So let's try it out with a couple of examples. So here I've called this encode function of this model, which has a lot of different parameters that you might want to look, but the defaults are already pretty good. And here we can pass either a string or a list of string, and then it will give us the embeddings back. And if we look at the shape of these embeddings, it's 512 dimension embeddings. And if we pass this input as a list, now the shape of the embeddings is 2 times 512. So because we have two inputs, for each of the input, we have 512 dimension vector. Now let's look at how we can encode images as well. So this is one of the images that we have in our folder called images, right? And just to show here in a small size, I resize it, and then we can see this image here. So we can directly pass this image to the encode function of the model, and the sentence transformers library will take care of pre-processing. So as we can see here, the image embeddings, we again received same 512 dimension vector. And if we pass a list of images, so let's pass the same image twice, then again we get the same thing. For every image that we pass, we get a 512 dimension vector. Now the reason we're using this clip model and not any other model is because the clip model was jointly trained to find similarities in both text and images. Because of that reason, we can do text to image similarity and also image to text similarity, and image to image as well as text to text. Now that we have looked at the basics of how to use the model and generate the embeddings, let's go ahead with the implementation part. So first, let's create this app.py file, which will be our main entry point for the Streamlit application. We'll just print out a hello world in the beginning. And to run this, we will do, let's open this here. So we'll open this side by side so we can see how our application progresses. This app.py file will be our entry point where we will do the searching. So basically this will be an inference space where you can go and search for similar images. I want to make another page where you can build these indexes. So remember that I mentioned 2 steps that we have to do. So we will do the implementation of the first step about building the indexes in the other page of this Streamlit application. So for the Streamlit, usually the pattern here is if you have pages folder, and any Python file that you create here will be listed as a page in the Streamlit. Let's call this settings.py. So if we look in the browser, we can see these 2 pages. The name of the pages will be generated according to the name of the file that you have given. So this is the app and this is the settings. There are a few things we have to implement. First, we need to read all of the file path of the images in a given folder because we want to read all of the images there. Next, we want to load the images. And then after loading them, we want to extract the embeddings from the model. And once we have the embeddings, we want to generate the KNN index and save it. There are a few imports we have to do. Okay, first we need to find the path of the images in given a directory, right? So let's implement that function. So this function will accept the folder where we want to look for the images, and the patterns will be what are the extensions that we want to read as files. In a folder, there can be different kinds of files. We don't want to read all of them, right? Here, basically, we're looping through the patterns that we have defined, and then using the glob function of the path object, we will find the paths that are present in this directory. And then if the path is a file, then we will put it in the list and then return them together. So our find images function is done. Next, we want to implement the load images. This function is pretty simple. So we just loop through all of the paths given to this function and then use the image.open function. Now just to try these functions out, so let's use it. And as we can see here, we can load the images and it's shown in the UI as well. Okay, so let's remove this one. Now we can load the image as well. We need to extract the embeddings using the model. So let's implement a function. So the signature of this function is the model is the first parameter that we have to pass. And the images that we loaded, the PIL images, and also the batch size. By default, it will be 32. And ultimately, this will return a NumPy array. The implementation is also very simple. As we saw before, we just need to call the model.encode function. Okay, so we have now 3 basic building blocks for our first step. Now let's piece all of these things together into a function called createIndex, which we will use later on. So first we find the images that are in the folder that is given here. And then let's just print out how many images are actually in that folder. Next, we will build this kind of a vector DB. It's not exactly vector DB, but a nearest neighbor index. This easyknn library has this builder instance that we can use to gradually add the embeddings as we generate them, and then it will allow us to create the nearest neighbors index later on. Since in a folder we can have thousands of images, right? We don't want to load all of them in the memory at once. So we will load them as we need. So we'll use the library called toolz or toolz, and then use a function called partition all, which will create a batch or a mini batch. So the partition all function creates mini batches. So in this image paths batch, we will have at maximum the batch size number of image paths. So batch size usually would be about 32, for example, by default. So at a given point, we will only load 32 images from the disk and then generate the embeddings. So now let's load the images. Now that we have the embeddings, we have to use this builder to add those embeddings along with the image metadata. So we can call builder.add, and it accepts 2 parameters. One is the embeddings, of course, and the second one is items. So this is the metadata that you want to attach to every vector or every embedding. So here in this case, I want to attach the path of the image as the metadata. And once we are done with all of the image paths in the folder, we will finally create a knn index and then return it. Now let's create the UI for this creating the index and also choosing an index. Okay, so this is the skeleton of the UI. Let's just save it and see how it looks like. Since there is no easy way in Streamlit to select a folder, what I've decided to do is list down all the folders that are in the current working directory and then create a combo box so that I can just pick one folder easily. So now I use the select box widget in Streamlit to show all of these paths that can be chosen, right? So as the options, the valid path is there, and as the format function, I just extract the name of the path so that it looks nicer in the UI. And as you can see here, we can select these folders. So in our case, it will be images because these two directory, they don't have any images. So I can just choose it and click the create button. So in this variable, we'll get the path that the user has currently chosen. So once we have that, we can, and once the user also clicks the create button, then we can go ahead and proceed with creating the index. So it will save the index along with the metadata in this path that we're given. And let's just write a success message. And let's delete the model from memory. So let's see how it works. So I've already chosen the images folder right now. As you can see, there's images, UI, and UI2 folder. So let's hit create. And if I open up the console, so it found 1033 images and it's doing its thing. And we can see the images index folder was created. So this is where the easyknn library stored the embeddings as well as the metadata here. So now that this is done, let's also quickly implement a mechanism to select which index we want to use. Once the user chooses the index directory and then clicks the submit button, we will store this in Streamlit session because we also want to access this path in the space as well. So let's see how this thing looks like. So we already created an index, so we don't need to do anything here. And now we need to choose the index. Let's choose this folder where our index is and then choose. So now our first step is done. So we have generated the embeddings and also created an index. So let's see how we can use that. First, I'll quickly import the necessary libraries. Now we need a couple of functions that can load the index and as well as the model in memory. Caching can be done by a couple of mechanisms. One is cache data decorator, and there's another one called cache resource, which we will use for the model. Cache data will use for the index. You can look up the differences between these two in the Streamlit's documentation. Okay, now let's implement the skeleton of the UI, and then slowly we will implement the searching functionality. So currently this is blank because we have already chosen the index directory from the settings page earlier. So let's add the other stuff now. Okay, now we are ready to implement the UI for searching the images. First, we'll implement text to image search where the user can input text as the query, and then we will find similar images from our index. So here what we have done is the prompt. Right now this is a text. As we saw earlier, we need to call the encode function to get the embeddings. And using these embeddings, we can then perform nearest neighbor search on this index. There's also another parameter called k, which indicates how many results you want. By default, it is 10, and I'll just leave it as it is. And the neighbors function returns a tuple. The first item is the image metadata, and the second one is the distance scores. Like if the distance is 0, then that means the query and the candidate that was selected, they have exactly the same content, or basically they are the same. The higher the distance, the more dissimilar they are. So we have implemented find by prompt function. Now let's implement this display results thing. Okay, our find by prompt and display results function is also complete. So let's go here, and we have argument missing. So okay, we need to do this, and let's see if it works or not. So source prompt, I know that there are some images with dogs, for example, and once I hit enter, we can see the images of the dogs. Let's try some more. So as we can see, the results look pretty good. So it seems to do pretty good. Like it can understand even a single word or multiple words and give back pretty decent results. Let's try one more. Pencil sketch, very nice. Okay, so we have implemented the text to image source. Now let's implement image to image source. For image to image search, let's implement this functionality where a user can upload an image, and then based on that image, we will find the similar images in the index and then display them to the user. And we'll also implement another way to find the similar images based on the images that are already in the index. The use case for this might be if you want to deduplicate, like for example, let's say you have lots of photographs and you want to find very similar images in your dataset. You don't necessarily want to use keyword search or something, but if you have a particular image in your index and you want to find other similar images in the same index, then this can also be used. So let's implement both of those. Before we add the other wizard to upload the images and perform the search on external image as well, let's first implement this and see how it looks like. So let's first create a button. The implementation is pretty easy. So the easyknn already has the neighbors by index function. So, and it will return the same tuple as before. And if we save this, so we should see the error disappear now. And let's say we do the search based on the first image, and we see the image results are pretty same to the input. Let's try this one. So the input is this pencil sketch image of, I think, Tom Hanks, and we see the same, very similar results. Here the first result is of course the same image as this one. Okay, so we have implemented this first kind of image to image search. Now let's also implement another one where we can upload completely different image that is not present in the index at all. So here we didn't have to implement anything extra because we can just reuse the find by prompt function that we implemented earlier. So a prompt can be both text and image, right? So in this case, the prompt is input image. And let's see how this thing looks like. Let me choose an image. There seems to be something wrong with the simple browser in VS Code here. Let me open this in Chrome and then show you how it looks like there. Okay, I have opened the Streamlit application in Chrome. Since I reloaded this, it will give me a warning saying the no image index selected. So first I'll go to settings and then choose the index that I want to use. And if I go to the app page now, and then choose one image that I have, and then search. So this was my input image, and it returned similar looking flowers. So in about 150 lines of code, we implemented image search application. I hope this video was useful, and that's all I wanted to showcase today. Thanks for watching. Bye-bye.